Hello, my name is Daniel Moth, and in this video I'm going to give you a glimpse as to what is new for parallel programming in Visual Studio 2010. I'm going to show you a bit on the APIs, a bit on the profiler, and a bit on the debugger as well, so a bit of everything. I'm going to do that using this application here, the C# application, which has 4 different approaches to matrix multiplication. And what we're going to see is how long each one takes. That's what this console application is going to put on the console, so keep an eye for that. What I also want you to keep an eye on is the CPU usage. So unfortunately already it is up because I'm recording, so that takes quite a bit of my CPU. But you should notice that the first approach will use only 1 core and the other 3 will use all 4, because the other 3 approaches are parallel approaches. So let's go and run it up so you can see what I mean. So the sequential matrix multiplication uses 1 core, like I said, and takes just over 4 seconds. The second approach is much faster and used all the cores. The third one also managed to use 100%, and the last one also will use 100% of the CPU. So you can also see that in the graphs. So the moral here is the results that we got, that the 3 parallel approaches were much faster than the serial approach, which was the first one, and also that the second approach is the fastest of them all. You can run this as many times as you want, that will always be faster, and these last 2, sometimes one will be faster, sometimes the other, they're basically the same with this micro benchmarking that I'm doing over here. So okay, that's what the results are, and we got that by using a stopwatch encode and capturing the times, and by also looking at the task manager. So let's go and have a look at the code itself and see what it does, just so we can understand it a bit better. So like I said, there are 2 code files here. There's a program.cs and the mmcs, the matrix multiplication file. And there's also VSP, which is the output of the profiling session, and I'm going to show you that in a bit. We don't have to worry about it now. So for now, let me just go and maximize this so you can see it better, and let's put them side by side. So what we have here, let's look at the program file first. We're in release mode, so we're using the size of 768, a random number I picked there. Later we'll switch to debug to look at the debugger, and then I've declared here 6 2-dimensional integer arrays, and they have the size of size. I've named these M1 and M2. Those are going to be the input arrays, and they'll be multiplied by these functions over there, and then the results of each one is stored in a different array over here. So how do we use this file here that has all the code from this file over here? There's only one function, the entry point main, and what I do in here is first I populate M1 and M2, and I populate those by using a random number, which I give it a random seed. And then once I have these 2, I can now pass them into those functions. And the way I do that is in these 4 regions. So we have a stopwatch that we're declaring and we're going to use, and then in the end we wait on the console. So how does the sequential code look like here? Well, first I put out on the screen sequential. You saw that. Then I get my new stopwatch, and then I go and call on mmulsec, which is that first method over there. And I pass in the size, I pass in the 2 arrays M1 and M2, and I get the results in res1. Then I put out on the screen how many milliseconds that took to string, and you saw that appear after the sequential earlier on. Then I sleep for 2 seconds. So 2 seconds later, we go and kick off the other approach. If you look at this code, it's boilerplate. It's exactly the same as the one above, except we put parallel 4 instead of sequential, and we call mulp4 instead of mulsec, and then we also get the results in res2 rather than res1. That's all that is different. The rest is identical. And if you go here, you'll see the pattern. In my third approach that are named tasks, you can see tasks, it calls multask, gets the result in res3. Everything else is boilerplate, the same as above. And the final approach, no surprises here. This is the thread pool label that I'm using. Mulpool passing in the same stuff, but getting the results out in res4. And that's how we saw each one of these approaches. And you'll remember that the first one was the slowest, obviously, because it's only using 1 core, and the other 3 are parallel implementations that I'm going to show you soon, this one being the fastest of them all, and these 2 being about equal. So right now I'm sure you're all dying to go and have a look at what does that code look like, but before we do that, what I like to do is go and show you the profiler. So I've captured here a trace earlier on, so you don't have to watch me catch it again, but just so you know how you're going to go and catch it, you're going to go on the Analyze menu, choose Launch Performance Wizard, choose Concurrency, visualize the behavior of a multi-threaded application, and keep hitting Next. That's all you need to do. So I've done that already earlier, and what I can show you here is the 3 views that the profiler shows us for multi-threaded applications. First, you have the CPU utilization view. In the CPU utilization view, you can see the legend here, and you can read that yourself. You have the idle time that your application is using on the cores. So you have 1, 2, 3, 4 cores. That's how many cores I have on this machine. You have the execution time. So the green is execution of your application. So clearly we can see here that at the beginning it used only 1 core. That must be our serial approach. And then the other 3 approaches all used 4 cores. So you can see that very clearly here. And then what you have is this other processes running. So clearly there's interference here on the system. You're not owning the cores. Other apps are using them as well. So it's very useful to see when they impact your application, so you can understand if that's the reason you're not getting the speed up that you're looking for instead of your algorithm. Maybe other processes are taking up your time, like antivirus, for example. So, and then if I go and zoom in further, so I can zoom in using this toolbar up here, and I can also zoom in if I just select, drag and select, I can see this other color, which is the system. So the system can also use the cores, and we differentiate that from other processes. So to help you go and investigate if you need to do that. Let me zoom out all the way. So that is what this view is showing you, the CPU utilization. It's the first thing that you see, and you see milliseconds down at the bottom, logical cores at the left, like I showed you. If I go and zoom in on this area here, now if I switch to any of the other views, they're also going to be zoomed in. So let me just go, you see the slider is moved as I zoomed in. So if I go to the cores view, you'll see that the slider remains zoomed in. So if I go and zoom it out, then we zoom all the way out. So zoom in is persisted across the various different views. So what can we see here in the core view? Well, what we see in the cores view is cores per swim lane. So again, I have 4 cores, so each swim lane is a core. And each color is a different thread. So let me just go and zoom in here a bit. So we zoom in further so we can see it even clearer, and I can see here that this thread 1348, which I happen to know is my main thread, this has been jumping cores as it was executing. Now maybe you don't care about that, or maybe you do, depending on the application that you're writing. So if you do care about cross-logical core context switches, then yes, this is a very useful view. If I go further down to the right, and we're here at 4.5, so about 6.5, 2 seconds later, remember we started the other approach, I can see this approach here, and let me just zoom in a bit more. Now this also has an enclosing border, which says parallel.4. So we see that second superior approach in matrix multiplication that I'm going to show you the code for in a minute, actually is, the tool is aware of it. So you can tell me, look, this is the region where you use that approach. So this is pretty cool, and you'll see later what that approach is like. So what am I seeing here? What I'm seeing here is 4 threads, sorry. So I've got 1 thread here, each color is a different thread, 1 from there and 1 there. And the only migration I'm seeing here is that this thread, it's in the end actually went to that core. So I'm not that worried about that. I can move on. So if I go further down, another 2 seconds down, so between 7.5 and 8, so that means between 9.5 and 10, we can see the third approach, which was slightly slower, and this is also used all the cores, which is a good thing. But what I can see here is I have cross core migration, so 1 thread is actually migrate across the cores, and also I can see that we have 5 threads if you count the colors. So 1 additional thread was used, which is not optimal for a compute bound operation like the one I'm doing now. It's purely compute bound, and it's on 4 cores, so why have 5 threads? And of course you can zoom in further here and look at more detail if that's what you want to do. And if I just zoom out, so I can go and find the last approach, which is the one over here. And when we go here, we can see that again, like the third approach, this is the what we call the thread pool approach. It also has 5 threads, and it also has core migration. This thread here jumped up there, but also the green one jumped there and then jumped back. So this is again is not ideal, but not something that I'm worried about in this application. It may have something to do, though. It actually may explain why this approach was faster than the others, right? So if you're interested in the cross-core migration stuff, the core view is the one you care about. And again, you zoom in on one view. When you go to another view, like back to the CPU utilization, that will be zoomed in at that same level. So let's go and quickly see the last view. I'm just going to zoom all the way out again, which is threads. And this is the most complicated that I'm going to let you explore in your own time. I'll just give you a starter. So what you're seeing here is each swim lane is actually a thread. The first 2 are disk reads and writes, and all the others are all the threads in your application. The different colors are different states of the threads. So, and I'll explain that in a second. So each swim lane is a thread, and they're ordered by start time. So I can see that at this time this thread was created, and so was that one, and further down that one was created then, and so on. So you can actually see when these threads were created in your application. You can sort by difference, so you can sort by execution time, which is what the green means. So if I sort by that, you'll see that it sorts them differently. If I go and sort by sleeping, we'll see that I guess that's the same kind of view that we have over here. And what I can do is I can also reorder these on my own. So I could go and click this guy and say, look, I want to move this further up. So you can reorder these if you have many threads. That's useful to go and bring the ones you want closer together. What you can also do is hide. So I can go here and control click to select quite a few. I could move them all together, move them all to the top, bottom, but I can just go and just hide them. So that will get rid of those threads, which I know are just .NET threads that are not doing much that I asked them to do. So I don't care about them. I can hide them. The other thing I can do here, of course, is zoom, just like I could in all the other views. And what I can also do is I can go and measure. So I could go here and click on my on the measuring device, and I can go and measure from here to here. How long is that? If I'm interested in that period, and you can see that this updates with the time that that period that I was measuring is. So I can see how long was it executing, for example, or how long was it blocked, was a thread blocked, and so on. Let me just get rid of the measure and zoom out again. The other thing we can see is again that enclosing boundary that we saw in the cores view. So this shows me that there's a parallel 4 that took place here. And in fact, if you go and look at this entire thing, here is the green, which is executing. So that executed that was my main thread executing the serial approach. Then remember there was a sleep. Well, here it is. So if I click here, I see the tooltip. It says thread sleep, and I can actually see that call stack. If I go and bring back the information that we have down at the bottom, I can see here that it is an mscorelib, a call to system thread in thread sleep. Here in this region is obviously my parallel 4, my approach that was faster than all and used 4 threads. So here are my 4 executing threads, and if I zoom in a bit more there, I can click somewhere and I can see that indeed this is the malp4. That's the function that it's calling. If I go further to the right, what is this? Another sleep. There we go. If I go a bit further to the right, this is where we're getting into the other approach. Again, I can see the call stacks down here. You get the idea. Basically, on this view, you can go and click, zoom in, and click on the various areas, and you can see exactly what your thread was executing by looking at the call stacks. It gets really cool when you start looking at blocking states, which I didn't have any by design in my application, and then you can go and see what the unblocking call stack was. So you can see this thread was blocked on, and then it starts running. Why was that? What was it that caused it? And you can see which thread actually caused it, and you get little lines here to help you with that. So I'm going to let you explore all that on your own. I'll just leave you with one final tip. The colors that you see up there are the ones down here on the left. So that's your guide, and you can see the percentages. But what you can also see here, just by clicking on them, you get detailed reports as to, and you can go and expand in there and see exactly where your threads were executing, where they were waiting on synchronization, where there was I/O, where they were sleeping, and so on. So to go click on these, examine the reports, click on the diagram to examine the call stacks, find blocking threads to look at the unblocking call stacks, and don't forget to look at the hints and hit the demystify button so you can go and understand how this UI works if you feel that you're at a loss at any moment in time. So those were the 3 views of the profiler. Now let's go back and look at the code again. So let's get rid of our VSP file over here. We've seen program CS, so we know what that does. Let's go and open the MMCS and have a look at the code in here. So we have here the sequential approach, which we called first. And what all that does is it has 3 nested for loops, and basically it does the matrix multiplication. It takes M1 and M2, iterates given the size that we passed in, and stores the result in the result over here. So that's fairly straightforward. You can study that in your own time if you feel like it. So how can I parallelize that? Well, I want to take advantage of all the cores, which means that ultimately threads will have to be created. So a naive approach would be to go and explicitly create threads. Now, we definitely don't want to do that. We discourage people from explicitly creating their own threads, unless they're writing their own thread pool, of course, which is another thing we discourage. So what you want to do is actually, the clue was in my previous statement, you want to use the thread pool. So today, without .NET 4, you can just go and use the thread pool. And that's the approach that I have down here. So what is it that we need to do? Well, if you think about it, this thing over here is actually independent. For each iteration is independent from all other iterations. So this can go on its own thread. So I could wrap this, again, a naive approach using the thread pool. I could wrap that in a call to the thread pool. I could say thread pool, go and do that. Every time I go in, just ask the thread pool to go and run that piece of code. And that's what I'm doing down here. So if we go and look at this, we'll see that in here is the inner loop, right? This is identical. I haven't changed a single thing. And all I've done is wrapped it with a call to thread pool queue user work item. And I've done that for each iteration in the outer loop. Now, the other thing I've had to do here is instead of using I directly from the outer loop, I created a temporary variable, and that has to do with enough to do with threading. That's just the way that something to do with the way that for each variables are captured in enclosures here in C#. So I've used that temporary variable. You can ignore that. I've basically wrapped the inner loop into that thread pool thing. And if we just want to go and have a quick look on that again, right? So just to make sure that it's exactly the same, you can see it over here. So that's the sequential approach, and that's what I've put in here in the thread pool. Okay, so we've done that, but there was more code, wasn't there? So what's up with that? Well, if I was to just leave it at that, just wrap it and let it go, then the main thread would come in here. It would go around in this loop, keep firing the thread pool, and then once it fired all requests, before they had completed, it would come down to the end and then would exit. So that changed the semantics of what the function did before. So for that reason, what I want to do is I want the main thread to wait and not return from this method until all the work has completed. So how can I do that? Well, unfortunately, the thread pool queues_work item doesn't have a rich API. It just returns a boolean, which is not much use, and there's only two overloads, one that takes state and one that doesn't. So there isn't a rich API here to use. So what I can do is I have to now know more concepts. So I have to know that the way I can block the thread, my main thread, is on some synchronization primitive. So I have to know, for example, about manual reset events. So I've created here one, and then I go in my main thread. After it executes everything, I'm just going to wait on it. So my main thread is blocked at this state. And it's going to be blocked until someone signals that manual reset event. So when do I want to signal that? Well, I want to signal that whenever the all work is completed. Again, there's no rich API here. I don't know when it's completed. So what I need to do is keep a count of how many of these I've queued. Well, I know how many. It's the size. So just store the size into the variable here, the iterations. And what I'm going to do is, I'm thinking here very cleverly, I'm going to go and decrement that every time that this work completes. So every time this completes, my next statement is going to be an iters minus minus. But of course, if I do that, there's a race here because this variable can be accessed by multiple threads. So there's a potential race here, so I have to use something safe. So again, the concept count goes up. Now I have to know about this interlock thing over here, which performs atomically this operation. So I'm using that, and when that reaches 0, so all threads have executed their work, only then that's going to signal the main thread to complete. So that's the way I've parallelized this, and we got very good performance out of that. So this is fine, except it's slightly naive that we're firing a request to the thread pool for every single iteration. And it's also, the concept count is high and the API is very poor. I have to know multiple different classes in the system threading namespace. Okay, so that was the fourth approach, which was using the thread pool, the pool. So now I'm going to show you this task approach. And remember, this is the same performance as that one, effectively. So why do we need it? Well, the reason we need this other approach is because of richness of the API. Let's have a look at it. Again, just like we did with the thread pool when we went from the serial case, all I'm doing here is I'm using this new API. So now we're new in .NET 4. The task class, it has a static factory property that returns a factory in which I can call start new. This entire thing, you can think of it as the equivalent of a thread pool queue user work item. So I'm just starting a job, and all I've done in the job is I've wrapped the inner two for loops, just like I did for the thread pool. Now the difference here is that this actually returns a task. And what I do with that task is I store it in an array. So I've declared an array of tasks there, and I'm storing it in the array. And then if I want to wait on the main thread, like we said, so I can preserve the semantics, all I have to do is go on task again, find the static method waits all, pass it in the array, and now the main thread will block. So the concept count is lower. I don't need to know about manual reset events. I don't need to know about interlocked. The code is cleaner, and we are using the rich API of a nice, object-oriented model that we have here. And the API is much, much richer than what you're seeing in this very, very simple example. So here I have a task. If I just go and use IntelliSense, you can see some of the things that it offers. So you can pass state into there, and you can access it at any given moment in time. You can go and use continuations, so like asynchronous waits. You can pass various different creation options in there. Exception handle is integrated into this API. Each task has a unique ID that you can use to cross-reference with debugger windows and other outputs. You can go and query whether it's completed or it faulted with an exception, or whether it was cancelled, so cancellation is built in. You can run things inline on the threads instead of starting them and having a thread pool thread pick them up. You can go and call start if you just created it and didn't actually use the factory to start it, and you can get a very detailed status as well as waiting on that piece of work that you've started executing asynchronously. So very, very rich API. Now what you also saw down here, I used wait all, and here I used the factory. So the task class itself has various methods. It also has wait any, so you could wait on many tasks, and when any completes, then you would continue. And at any moment in time, you can get the current ID of a task executing when you make this call there. On the factory, you've seen start new, so you can start tasks in a single go. And there's various cancellation stuff in here. But what's really cool is the from async method, which integrates this new task parallel library API with the older asynchronous programming model that's based on iasync results. So if you've got existing code that uses iasync results, go and check out the from async methods. You'll be pleased. And for the really advanced scenarios, you can even write custom schedulers that schedule things in a way that you feel is right. So definitely go and explore the API. It has the same performance characteristics as the vanilla thread pool, but a much, much richer API to play with. The official guidance is always use tasks by default instead of the thread pool queue user work item. Only fall back to that if you're really sure that you don't need any of the API expressiveness that the task API offers. So what we're going to do now is go and debug this application, so you can see some of the debugging features. We're now running in release mode. If I go and change that to debug mode, we'll have less data to work with, which will keep things simple. And then what I want to do is have a breakpoint. So I'm going to go here and very quickly type this line of code and put a breakpoint on it. So it's simply a debug write line itself. So now let's go and hit F5 to run this guy up. So it's running up. The numbers now don't matter at all. We're using a smaller set. And now what we can go here and see is the threads running in this application. So that's what you would expect to see if you were using threads. You'd see each thread here. There's 4 running in addition to the main thread. I can see the call stack. They're all in the anonymous methods. I can switch between the various different threads to find where they are. But we have a better window to actually show you what all the call stacks of all your threads look like in a single view. So if you go to the debug menu, you can open parallel stacks. So here is the parallel stacks window. What this shows me here is that I have one thread, and I can go and see that that's the main thread. It's thread 504, and I can see that that started in main, then called my mal task, and I can see the arguments that were passed to it. And then I can see that it called task wait all at some point, and that called other internal stuff further down. So then that is what I expected, right? So if I just switch to it, you'll see that that's where it is. What this other view is showing me here is that I have 4 different threads, and I can see exactly where they are. I can switch to that, and I can see that these 4 threads are these IDs over here. They're the worker threads, and all of them share the same call path. They all started, there's some thread pool threads, but actually they are task. They're calling internal task methods, and they end up in my code in the mal task anonymous method 3. So that's the method that I've got there. And looking at the line numbers, one of them, this one, is at that place. The other 3 are in at line 57, all of them. So if I just switch to that, we'll be able to see that's where they all are. They're all the debug write line. So very useful view. I have done a whole screencast dedicated on this, a 15-minute screencast, so you can go and learn more about the parallel stacks window and its various toolbar options and the various context menu items that you got over here. So go and explore that in your own time. I hope you can see the core value that it brings here, showing you everything in a single view. But we're talking about threads when actually we created tasks. And for that, we have another window, which is the debug window parallel tasks. And I've done a whole screencast on that I encourage you to go watch. I'm just going to briefly show you its value over here. So what is this showing me? Well, this is showing me now tasks instead of actually threads. So I can go here and remove columns that we don't want to focus on right now. I can go and reorder them, so I can bring this thread assignment column to the front. And then what I can see fairly clearly is that we have these 4 tasks running on these 4 threads, just like we could see earlier. And I have a whole bunch of scheduled tasks down there. Now what I can do here to manage this a bit better is I can group on any column. So in addition to adding, removing, reordering, sorting, we can go group. So if I group on the status, then I see here that I got 196 scheduled tasks. So let me just collapse this group. There's nothing else beyond it. Good. So 196 plus 4, that's the 200 tasks. The 4 started executing, and the other 196 are scheduled to be run. This is information you could not see before. If I want to, I can go and see other information like IDs and so on. So okay, I've got 4 of them running here. I've collapsed that group. Let me just go and hit F5 to go through another iteration. So as I'm doing that, you'll see that the count here updates. So I'm just going to keep clicking through, and we can see that as tasks complete, other scheduled tasks are running. So the thread IDs change, and so on and so forth. Now, at this interesting point that I've continued, we can see that one of the task status is not scheduled, it's not running, it's actually waiting. So I've got this task here, which is waiting. And I would wonder what it's waiting on. Now, I could use the threads view to find that, but if we go to the tasks view of the parallel stacks window, it becomes very clear very quickly once you know how to read this diagram, of course. So what this thing here is telling me is that you got 4 tasks, and one of them is running in this box, and the other 3 have so 2 of them are actually running in this box, and the other 2 have progressed. And of those 2, one of them at least is waiting, the other at least is running. So in this case, one is waiting, one is running, and they're both in debug write line. So this is very clear. We've called debug write line. This is an API we do not own. It's owned by someone else, in this case the framework. And the debug write line must be taking a lock in there, which means that one task is blocked. You don't want to have this because that inhibits the parallelism gains you can gain. If you have a thread blocked, a task blocked, and its thread blocked on a synchronization primitive, then of course you're not using the course. Remember, of course, debug write line was not there in the release mode, so this didn't affect our performance measurements. So if you had the parallel stacks window open, immediately this would attract your attention. You'd know, oh, I've got something here I need to investigate. You would then open the parallel task window. We did them kind of the other way around, and then here you can see exactly which one it is. You can switch to it, and more importantly, if you go here on the waiting, you can see a tooltip, and it says, look, this is waiting on some object which is owned by thread 4872, and if I see up here, that is thread 4872. So I could just flag that and flag that one, just so I can keep an eye on those 2. So those are the 2 threads. That one has the lock, and that one is actually waiting for it. If I go and show flagged threads only, we can see that flagged tasks only. Sorry, we can see that even clearly. They were both executing there, and then they went in there. If you want to see the detail of exactly what happens in the framework, this is not your code. You've already identified the issue. Basically, don't use that API. But if you wanted to actually see further, if you were the owner of that, you can switch to threads view, and there you can actually see how all of this happens. So debug write line is calling internally trace internal write line, and then there you go, you're waiting on the monitor on thread 1056, which is the one assigned to that task, and obviously who has that monitor? The one that got it is the other thread up here, 4872, which is the one executing that task. So here you're using more screen real estate to see more detail into internal framework methods, which typically you wouldn't care about. But if you do care about that and you want to see it in the task view as well, you can. If you just turn off just my code, you would see that picture here as well of fanning out into 2 branches. So that's just a quick glimpse I wanted to give you into the debugging support we have for tasks. So I was talking earlier about the rich API, but now you can see that what goes in addition to the rich API is rich debugging, making task-based programming a first-class citizen in the debugging experience. So it's, again, another reason to use this instead of the thread pool, for example. Okay, so let's go and stop this guy. So we've seen debugging, we've seen profiling, we've seen the task-based API. The final thing that you want to see is the parallel for, which the profiler was aware of as well, which also uses tasks under the covers, I can tell you that much. So what is it doing? Well, what you can see here is that we want to take the inner loop and just execute that. And we're thinking how we can use threads and so on. There's a much simpler approach. You simply go and put parallel.for, so you make a call to this new API, and you pass in just like you had earlier. So let me just go and make sure you can see all that on one screen. So you pass in 0 up to size, and the variable is size. So it's exactly the same information, and then from then on the rest is identical. So we just change the one line over here to make a call for the outer loop, keep everything in the same inside, and of course in the end close the method call over here. So parallel for, does it do anything magic? Well, internally it partitions dynamically the data that is given, and it uses tasks under the cover, so you can debug this in exactly the same way in the debugger. And this gives you the simplest API to use and the best performance to get out of it. So you get the best of both worlds. And if you want more rich API here to do other stuff, there is some flexibility in the form of 12 overloads, so you can go and explore those and see more powerful things you can do with parallel.for. And don't forget to look at its parallel for each and parallel invoke as well, which are other methods on the parallel class, part of the task parallel library. So with that, I'm going to stop this video here. I hope you enjoyed this very quick tour of what we're doing for parallel programming. Everything I've showed you is also available for the native developers using the parallel patterns library and the concurrency runtime, and the profiler and debugging support is the same for those models as well. Thanks for watching, and as always, if you have any questions, please email me at daniel.moth@microsoft.com. Thank you.